So I think I'll start with Coxeter groups. Because if you don't end up, if I don't go far enough, then we might not need the links thing. So I'll come back to the links thing if we get that far. Okay. But I can just say one sentence, like I was saying, a space is locally cat 0, locally cat k, if the link condition is satisfied. Link condition, let me just say the statement. What does it mean to satisfy the link condition? That means that at every vertex, the link is cat 1. Let me just write the statement without really. So X is locally cat k, it can only the link at every vertex. Yeah, I don't have a lot of intuition to share why this is true. But knowing when things are cat1 is important. Somehow cat1 is special in that sense. So locally you can tell whether something polyhedral complex is cat k by just checking the link at every vertex. That link is cat. I was roughly trying to explain that how the link is the metric, but let me skip that for now. And if we get to the point where we need it again, then I'll remind you. Okay. So let's start with Coxeter. So let's start with a finite set S. And let M be a matrix. Be a symmetric X by S matrix with entries in N plus P and positive integers, and then infinity is also about funny. That M is 1 for every S in S and MST is at least 2 for S not infinity. And such a matrix is called a Coxeter matrix. A group is called a Coxeter group. If it has a presentation of the form S and then ST. The relations are ST raised to the power M for of S17. Yes. Where this MXT is an Coxeter matrix. And such a presentation is called a Coxeter presentation. The Coxeter system. WS. It's a Coxeter group of W. Such that there is the Coxeter matrix. And defined with respect to S, which gives me the Coxeter presentation. I'm basically defining a Coxeter group using a presentation.
What is that relation? ST to the MST?
ST raised to the power MST. So, okay.
Oh, okay. MSTs are numbers.
MSTs are numbers, yes. So you should think I'm starting with a matrix, starting with some real symmetric matrix. And what are the relations here? The relations are basically these. The powers are coming from that matrix. And Coxeter system is basically when I say W comma S, I just mean this group has a presentation, Coxeter presentation coming from using S as generic. Real symmetric meaning, so yeah, symmetric would be MST is the same as MT.
I'm asking.
Yeah, I'm going to do it. Now. So if S is just a singleton set, there's just one element, then I should, okay, the way I'm defining it, I should be thinking of a matrix first. So I'm just thinking of a 1 by 1 matrix. And this matrix just has to be one there. Okay, so the group here is just the Coxeter group here is just Z mod 2 span. Because that's the, yeah, X square is the only relationship. If S has two elements, S and T. Okay. What kind of matrix can I have? It needs to be one on the diagonals. And then it's symmetric, so I will just pick one number M. Okay, and then what's the presentation that I'm looking at? I'm looking at ST such that S square is 1, T square is 1, and ST raised to the power M is 1. So this is for M greater than equal to.
They're all the time diagonal groups.
No. If I have two elements, then yes, yeah. The two elements, like that's the only thing I can do. Yeah, and then, yeah. Like you said, these are dihedral groups. Um. Yes, maybe what? Let's isolate the case. So I'm still in this example, like M is two. If M is two, then the group that I'm looking at. What's the group that I'm looking at? D3. No, if M is two,
Then from two Z times Z.
then what two times that one, right? Because yeah, S and T are commuting. And if M is infinity. So yeah, I didn't say what infinity means, sorry. What does it mean if ST to the infinity? That means there's no relationship. I should have said that. What does it mean for MST to be infinity? Is there's no relationship between. So what's the, if M is infinity, what's this group? Sorry,
P product.
P product of?
Yes, get to
Yes. Is there a better name for that?
get to stars are two.
No, no.
Yeah, but I didn't.
Infinite dihedral group, right? That's what we call it. The infinity, which is Z mod 2 star Z mod 2, or like, I get the semi-direct product correct. I think did I get it? I don't know if the semi-direct is correct here or not.
I mean, other way,
Other way? Okay.
other same thing. I mean, Z is the normal component now.
Okay. Z is the normal, right? So it's always confusing to me how much is this. So then I wrote it correctly. So Z is a normal sum. Yeah, which one of us, basically what is D infinity? D infinity is a group of symmetries of, it's the symmetries of the real line with this kind of cellulation, right? Because what's the, if I give you this graph, this infinite graph with vertices and integers, this group of symmetries is exactly, you can either do two reflections, that this is, let's say this is 0, 1, -1. Yeah, so you can do two reflections, one about this 1/2 and one about -1/2. So that's this way of thinking about this. What's the other one? You can do one reflection and one translation. That's the infinite integration. And then if M is not 2 or infinity, then I'm really getting the dihedral group DM. Okay, symmetries of a M-sided polygon. Does everyone know? Because this is the same as we did this in the first talk. And you have RS. What is DM? RM S squared and SRS is our inverse, which I can rewrite as SR squared. So if I declare T to be SR, then these are the same. So these are all, so that dihedral groups are examples of. Okay. So now there are two ways of representing Coxeter groups. So that M V1 Coxeter matrix with respect to this finite set S. There's one thing which is called Coxeter graph or diagram. And the other thing is called a presentation. Presentation graph. So this was represented like this. This. What's the complement gap? The vertex set. The vertices are by finite set S. And two vertices are joined by an edge. D1, D2 are joined by an edge. Okay, let me write the sentence now. So. Two vertices joined by an edge. If the label is strictly bigger than 2 and are labeled and an edge is labeled, it's not equal to 3. So I think that these are just conventions. So you, guess I've drawn these matrices and we just draw these two graphs just to understand what they look like. I think this used to confuse me a lot. There was a time when I would try to look up Coxeter groups and people would draw these two different kinds of pictures and it would massively confuse me. Which picture am I reading? What's the presentation graph? The vertices are still S. And you put an edge. You put an edge if the label is strictly less than infinity, and you put a label. If it's not 2. So let me rewrite this in a shorter form. So when you put an edge, when the label is at least 2, and when do you put a label when the label is MST as long as it's not equal to 3. Is some convention. Maybe take a minute and just complete this table for yourself, just so that you can digest the whatever in there. After preparing for these talks, I appreciate a little more why we have these two different ways, only slightly more than before. But do you have a better answer for why there are these two?
Sorry.
Do you have an answer for why there are these two different ways of representing?
Well, I mean, both have the same information
Yeah,
and the graph, just by looking at the graph, you know what is MSP for.
Right.
So, yeah.
okay. Yeah, for me, this one's nice because seems like this is what I'm going to use most of the time.
Yeah.
But this will show up as the link of a vertex in this place that I will build.
Yeah, but both of them have exactly the same
Same
information. So, and to define a Coxeter group, that's all what you need, Coxeter matrix.
Right.
One information you can deduce that from the above graph. So if I from the Coxeter graph that will be fine. So if I'm taking the connected components of gamma S, then it will become a direct product of those factors. And here for the presentation graph, it will be free product of the.
Right, yeah, that's a very good point, because no edges here means. No edges means the label is 2. Sorry, the elements commute. So if you have two connected components, then everything here commutes with everything here. So you have a direct product. So that's one nice thing you can read from this circle. This is connected, then you have direct product. Whereas over here, no edge means the label, like the order is infinite, meaning there's a free product. Okay, so that's one nice thing. So let's just quickly do
Well,
this.
maybe you should like just modify this. Say, for example, you won't have an edge. You won't have an edge if MST is infinity or MST is 2. Right, so I think.
No, I will put an edge if it's 2, but I will just not label it. I think the labeling is just to be lazy.
No, edge. He says there is an edge if MS2, this MST is less than infinity.
Yes.
And there is no edge if MST is equal to 2 also.
No, there is an edge if it's equal to 2 in the presentation graph, not in the Coxeter graph, but in the
Okay.
presentation graph there is. Yeah, that's what they are.
Yeah, okay.
So here S is always not equal to T. You know,
Whenever I write ST, they're not equal. So this picture is basically, there's no edge over here, but there is an edge here, which is not equal. When it's 3, there is an edge. There is also, there is an edge, understand? With infinity, there is a labeled edge. With infinity, there is no edge. Now let T and S be a finite subset. Now the group WP, the subgroup WP generated by T is called a special subset of W. Yeah, I'm starting with Coxeter system. I'll use my Coxeter group. This is the generating set with respect to which I have this Coxeter matrix, which will give me the Coxeter. Okay. And that, in fact, this W, so let gamma T be the full subgraph spanned by T in gamma X. Then WT is isomorphic to W gamma T. I guess my notation is basically what I want to say is the subgroup generated by T, you can read off from the subgraph. The subgraph is a Coxeter system for that T. That's what this fact is supposed to say. Okay. And you have a finite special subgroup of W is called clinical subgroup. Yes, basically I have some Coxeter diagram with some labels and N1 and 2 something. Yeah, I'm saying if you pick a finite, well, first I said just pick a finite subset of T, so I didn't pick this edge. I just picked the 2 points, right? I just picked those 2 points, that's a finite subset of S. Then I can look at the subgroup generated by these 2 things. And I'm saying the subgroup generated by these 2 things, it's Coxeter, it will be a Coxeter group. So this is all facts, like I'm not proving any of this. The subgroup generated by these 2 will also be a Coxeter group. And what will be its Coxeter matrix or Coxeter presentation? It will come exactly from taking the full subgraph, like the graph spanned by those vertices. And if this turns out to be finite, if this subgroup turns out to be finite, I call it spherical. So for instance, if there was if there's an N, an edge will always give me a finite. The only example we saw were these dihedral groups. So an edge always gives me a dihedral subgroup. No, I shouldn't say. And it always gives me, if M is not infinity, then it always gives me a finite dihedral. So those are those are always spherical. Okay,
Yeah, if M is infinity also, it is
it's a
diagonal.
dihedral group, but it's not finite. Yeah, so I would not call it spherical. Yeah. Okay. So now I want to give in the sense like, give a family of examples for Coxeter groups, which are called geometric reflection groups. So these are very hands-on in some sense, but then Coxeter groups are an abstract, I can call them abstract reflection groups. They are an abstractification of these geometric reflection groups that I'm going to tell you about. As examples. Okay. Let me define, I think in the last thought I wasn't defining some things carefully. Let me do that now. A Euclidean convex polytope is the compact intersection of finitely many half spaces. In Rn, someone. Okay, this we understand. Now I want to define a spherical convex polytope. Okay, I want to define this and I want to make the same definition, except I want to say half spaces in Sn, but then I have to tell you what do I mean by half spaces in Sn. So let me say that more carefully. So I want to view Sn as the unit sphere plus one. S2 sitting inside R3. And then a spherical hyperplane. So what should a spherical hyperplane be? I would like it to be, take a linear hyperplane. Take a linear hyperplane passing, like a hyperplane passing through the origin and look at its intersection with the sphere. That's what I would like a spherical hyperplane to be. Is the intersection of Sn with a hyperplane of n plus 1 passing through the origin. Okay. And then a spherical half space I can define. Spherical half space is, once I know what a spherical hyperplane is, spherical half space is basically take the complement of this hyperplane and take its closure. Okay, I'm really thinking of this as in this Rn plus 1.
Half space means you would take only one side, right? It's greater than.
Yeah. So for instance, here if I take the xy plane, xyz, the xy plane, the intersection with the sphere gives me a hyperplane, spherical hyperplane. And then what's a half space? It's like positive z's or the negative z's. That would be a half space for me. Spherical
Either
half
the
space.
positive or the.
Yeah. And a spherical convex polytope would be the intersection of compact intersection of finitely many half spaces. So for example, if I take my if I take my half spaces to be well, what's the right way to the xy plane, but then z plus, so the half space, xy plane is my hyperplane and z plus is the half space that I want to look at, okay, and then yz plane, x plus, xz plane, y plus. If I look at these half spaces on the sphere, can you say what picture are you getting? What part of the sphere did we get?
Right, the hemisphere on the, like you divide, cut into the two parts, left and right of x-axis, right part.
You're getting something smaller.
Hmm?
You're getting something smaller than, it's not a hemisphere.
Oh, you're taking the
Quadrant.
intersection?
Yeah.
Oh,
Yeah, it's the intersection, yeah, sorry. Intersection of all these. The convex polytope given by intersection of these half spaces, I'm really getting the picture I had drawn. Like I'm really getting. That quarter. Right? That's an example of a spherical polytope. Okay, what's a geometric reflection group? And then I can make a similar definition in hyperbolic convex polytope, but not going to do that. And geometric reflection group is a group generated by reflections in the sides of a convex polytope in Sn, En, or Hn, such that, so this is not enough, it is such that this convex polytope P is the fundamental domain, such that P is a fundamental domain. For the action of G. Okay, and then such a polytope, if I have a geometric reflection group for a polytope, then that polytope is called a Coxeter polytope. Okay, so let's there are exercises about figuring out these geometric reflection groups in small dimensions. But let me quickly, just so that I can give you some more examples, to give you give you a quick idea of what it can look like in small dimensions. Right. So I can do this in Sn or En. So let's let's not worry about Hn. So if I'm doing it in so let's do it in E1. Okay, E1 is just this line. What's a what's a convex polytope in E1? It's any interval, right? So let me take -1/2 to 1/2. Let me take this interval. And I want to do reflections in its sides. So that means I want to do one reflection here and one reflection here. So what group will I get? what will be the group generated by S1 and S2?
So two close.
Right, so the infinite dihedral. Right, so the group I'm getting here is the infinite dihedral. And I can scale I can choose bigger intervals or smaller intervals, but the group is the infinite dihedral. That's one. Let's do S1. Okay, I'm supposed to think of S1 as sitting inside R2. What's a convex polytope in S1?
Marcus.
R. Right, so I have arcs. Okay, let me just for it. Let me just draw this. Okay, this is an arc. And then I want to do reflections in its sides now. So, so again, I'm drawing it in the plane, but the reflection, there would be one reflection like this and one reflection like this. Okay. This arc is determined by this angle theta. Now, what mode do I want? I want to reflect in the sides of this convex polytope such that this arc is a fundamental domain for the action. So can you say something about this theta if this is supposed to be a fundamental domain for the action?
Rational.
Rational. Right.
Okay.
And integral submultiple of pi, right? Because what happens when I do this reflection? So I have this. Let's put a arrow on this. When I reflect, it goes to this guy. The orientation has changed, right? And then when I do this reflection, orientation has changed again. So if I keep doing these reflections, so let's see, this was S. If this was my P, this was S1P. Now if I do S2P, S2P will probably like will be somewhere here, and so on. But the upshot is there will be even number of these. How many copies of P will tile this circle? There will be even number of them. I have to come back to P. I have to have the correct orientation. Because every time I do a reflection, it goes from like this orientation to the opposite orientation. Orientations are changing. So it has to be some even number. So basically I'm saying, so what's the, okay, sorry, I'm claiming 2 theta is, no, if there are 2m copies of P tile S1. Okay, so basically that means theta is 2 pi by 12. So that's what I want to say. And in fact, so now I have these two reflections. And you can check that the order of like S1, S2 times M is trivial. So the group here is really the dihedral group. Yeah. And there'll be like this 2m sided polyhedron. So yeah. I shouldn't say more. But so in fact, theorem is that like one-dimensional reflection geometry. Reflection groups are in bijection mode. Dihedral groups. Okay. Okay, let's think of 2 dimensions. Okay, I'm not going to solve it, but just like let me give you an example. So we define this thing called a triangle group. A triangle group delta PQR is a Coxeter group. With matrix given by 1, 2. Okay, so I'm just abstractly I've told you it's some Coxeter group with this matrix. But let's do the first case. What case do I want? Let's assume P is 3, Q is 3, and R is also 3. So I'm just showing you this as an example. The exercise, hopefully we'll have some time for that exercise. The exercise basically tells you in 2 dimensions. It'll at least tell you in 2 dimensions which triangle groups are hyperbolic, which ones are Euclidean, which ones are spherical. Okay, but let me just do this one example. So for this example, I can realize this group as a geometric reflection group on E2. So delta E3 acts on E2 as a geometric reflection. Now, basically, but if you take 3 lines, and this is my polytope P, which is given by these half spaces. And then the hyperplanes are making an angle pi by 3. And I can tile the Euclidean plane. So if I do, so what are my 3 reflections? My reflections are S1, S2, and S3. Just reflect about these 3 lines. And this will give me a tiling of E2, right? Euclidean triangle like this does ideally. This is also an example of a geometric reflection group, or in particular a Coxeter group. You might have seen these. I can do. I'm going to write down this hyperbolic one. 2, 3, 7. Maybe you've seen this beautiful pictures of tilings of a disk by triangles. I can't draw it. But which triangles can you tile this by? That's exactly these numbers. And you can really tell what these numbers need to be for spherical, at least for spherical and Euclidean. It's a finite list. So these are also examples of, so these are infinite. Right, so here these were finite groups, finite Coxeter groups. This example is an example of an infinite Coxeter. Okay. And so basically, Coxeter was able to, so Coxeter was able to classify all Coxeter polyhedra in Sn, and those are all the finite Coxeter groups. So he classified all these Coxeter polyhedra in Sn and En, and this really gives you the classification of finite Coxeter groups. And this gives you the classification of affine Coxeter groups. And the part that I'm not going to talk about now, but it's in my notes, is at least for figuring out when a Coxeter polyhedra is a spherical polyhedra, you really just need to do some linear algebra. I think it's really beautiful that you just do some linear algebra and figure out whether a given polyhedron is a spherical polyhedron or not. And so you can, and it's a very checkable thing. It's not an abstract thing. You can really just like check it by hand or put it in a computer if you wish. And you can really check, at least for finite dimensions, for a given finite dimension. So yeah, so there is a list of finite Coxeter groups and affine Coxeter groups. So yeah, I was saying these geometric reflection groups are examples of Coxeter groups. So So geometric reflection groups are examples of Coxeter groups. But there are definitely Coxeter groups which are not geometric reflection groups. Not every Coxeter group, because Coxeter group was defined by just this abstract presentation. So you should think of them as abstract reflection groups. Even though the idea is coming from like you have these like honest geometric reflection groups on SNE and HN. But Coxeter groups need not always be reflections on these nice spaces. But the idea of this Davis complex, which now I should be able to tell you what the Davis complex is to come up with a space on which the group, my Coxeter group, is still acting by some kind of reflections. The space will not be this, the space will not be a sphere or Euclidean, it will not be one of these model spaces, but it will be a MK polyhedral complex. So that will make it more complicated, but I will still get my group to act by reflections on that space. So that's the goal. Yeah, I would encourage you to read, there's like a couple of pages in my notes. I really like it. I'm going to skip it right now. Any questions?
So when you say these are checkable, I mean, are there a specified algorithm by which you can?
So I can, let me say what the criteria is. So like if you are given a Coxeter polyhedron, one thing is just for spheres. So let me just say it for spheres. Okay. In my sample. Let's say I'm given a polytope P. First of all, if it's a spherical polytope, one has to prove it's always a simplex. So it's a simplex. And if it's a simplex, let's say you're given, there are two pieces of information you could be given. If it's a simplex, you could be given these dihedral angles. Like the angle between the codimension one faces. Or you could be given lengths of edges in that simplex. Those are two pieces of information you could be given. And using these numbers, you can write down a matrix. And all you have to do is check if that matrix is positive definite or not. And checking if your matrix is positive definite is like a very doable, checkable, it's a very checkable thing. Okay. So let me tell you what the Davis complex is. Then I think you can have some fun and draw Davis complex for a bunch of examples. That will be the exercise, which is very instructive, I think, to understand it. So so I'm given this Coxeter system by the gamma X. So I'll define three subsets. Script S would be the set of all subsets of S such that the Coxeter group generated by P is spherical. Remember, spherical basically meant finite. Then there will be this set, which will be, so P is allowed to be the empty set here, and here I just wanted to not be the empty set. And this is the union. So I take all the, so by this I mean all the cosets of WT. You look at all your spherical subgroups, and then you look at all their cosets. That's the set. Okay. We'll do an example, but let me just put it up here. So notice one thing, each of these sets is a partially ordered set. So this is just subsets of S. So there's clear partial order here by inclusion. Actually, everywhere, this partial ordering by inclusion. And whenever you have a partially ordered set, you can make a simplicial complex out of it. Right, so maybe, let me just say here, whenever I have a partially ordered set. What's the, so let's say I have a sequence, I have this chain, suppose in my partially ordered set. So I'll give myself a vertex for each of these. For each ordering, I give myself an edge. And whenever I see a simplex, I fill it in. That's how I make a simplicial complex out of partially ordered set. Okay. So then make, so let the simplex, simplicial complex. Let this be called K, let this be called L, and let this be called sigma. So this will be called the chamber. This will be called the link. And this will be called the Taylor's complex. Let's do an example just to see what's going on. So let's say this is my, let's say I've given the dihedral group T3. Okay. So what's the first set? What are all the subsets? Which give me spherical. So I have the empty set. I have just S, just E, and everything. That's also. And so what is K? I'm supposed to give myself vertices for these. So I have the empty set, I have S, I have E, and S E. And I'm supposed to put an edge if I see inclusion. Okay, so empty set is sitting inside all of them. And then S is in here and E is in. And I'm supposed to put in a 2 cell if I see a. So that's K. Chamber. Okay, I'm not going to write it, but if the empty set is not here, so the empty set is not here, then this is it. Okay. Now I want all the cosets of these things. Okay. Maybe I'll let you write them down. So why don't you write all the cosets and see if you get a partially ordered set. You know which T's to look at. You know which T's to look at. These are really these possibilities. I want you to look at all the cosets and see what's.
The last one admits empty set or not? The WS?
The WS T is still allowed to be empty. Yes. I'm just asking you to do basic group theory. I have subgroups and I want you to write down what are the cosets of these subgroups. I'm basically asking you to write down the cosets of WP. WP is the trivial group, right? WS, WP, and WST, which is the whole group. The rest of it. Once you have the cosets, also try to see if you can find a partially ordered, like a partial order. You can arrange them by partial order.
Can you compare with respect to the COSET represented?
I want like the full cosets, like, so maybe let me do the first two. So WP is just the trivial subgroup. So what are the cosets of the trivial subgroup? All the elements, right? So 1, S, E, S3, ES, STS, which is the same as PS. Right, so I have six elements here. What are the cosets of WS? WS is a subgroup generated by S. So its first coset, so okay, that's just WS. The one. S will just give you the same thing, and I have PWS. Right? And I have STWS. Then I can see I have containment, like S lives inside this guy. So S lives in here. Let's see. PS lives in here. And STS lives in here. I already have some edges. And if I do the thing for T I will get WP, this WP, PS, WP, and this is the whole group that take both S and T. There's only one coset. One column. Right? And now what's the partial order? Now clearly everything is contained in W. So if I want to draw my simplicial complex, there is that one vertex for W and everything is going to be connected to it. I already know that. So yeah, since I've drawn this picture before, I'm going to cheat and draw it nicely. But did anyone try to draw the partially like the simplicial complex? Okay, so let me I'll do. So I have the WS over WD. Like the vertices are for this guy, the vertices are supposed to be the cosets. So I'm just drawing cosets for those vertices. And I do have an edge here because identity is contained in here, here, and here. And then I also have this edge. Because S is contained in W, P is contained in W. This one is then B, FP gets. This guy will be. B. That is, and I have all these. I have all these edges and then these are all filled in. Basically, you have a hexagon. Right, and I've just like made it into a simple complex. But yeah, then what's the action before we move on?
So we have taken the first one. Those.
These ones? I did, I didn't write it the way I should have written it here, but this is one WP, one SWP, STWP. This guy, this guy. Yeah, so maybe let me color them big. These are the. Let's see how.
One is not. It's got 10 million, mod W and the. Yeah, three.
This should be an H. What's the action of S? So I'm saying this is going to be the Davis complex, except there are too many cells here, like hexagon is what I really care about, not all this like too many triangles in there. But before we do that, what's the action of S? What does S do? Okay, S is going to fix this. S is going to send this coset, this coset to this coset. Right? It's going to send, so what did it do? It did send this to this. S took this guy to this guy. S took this guy to this guy. Okay? S took this over here. S took this to this. And so on. So S is basically acting by reflection. S is acting by reflection about this line. And T is acting by reflection about this. And you'll see this is the fundamental domain. This is the fundamental domain for a question, which is exactly this K. So the point is that K, we are defining things, K is supposed to be fundamental domain. What's L? What's L in this picture? So if you think about the rough picture, rough idea of what I said a link is, what is a link? What is the link of this vertex? Link of this vertex is take a small neighborhood around this point. And then how is this? Yeah, just topologically, let's not worry about the metric, just topologically. Topologically, this is the link. And it, I mean, I could, if I just like take it further, this corresponds to WT, this corresponds to W, and this corresponds to WS. So this is exactly, I should cover it. So that L is supposed to be the link. L is supposed to be the link of a vertex. Okay, and then so this is supposed to be the Davis complex, except which I mean I can see from your faces, it's really like too many triangles. It feels confusing, right? To draw so many edges. So we will redefine it such that we can forget about all these edges in the middle. I want to recellulate decellulation. Decellulation. So for every T in S such that WT is spherical. And for every G in my group, we will build. So I'm going to define, so this was, this is called the Davis complex. I will define this thing by, I will build this thing by built by gluing cells of dimension P, how many elements in P? For each coset. Okay, so what's the if what are the vertices? Cells of dimension 0, which means P is empty. So the vertices will correspond to T and P, and I will give myself a vertex for all the cosets. So WP is trivial, and I basically have a vertex. Vertex corresponding to G T, like to cosets of GP, which are basically elements of P. Because I'm redefining my space. So it will be built out of cells of dimension dependent on T. So if I'm looking for dimension 0, P is empty, and all the cosets of WP correspond to the elements of G. So all the vertices correspond to elements of W. What do edges correspond to? Edges correspond to a single T has to be a single element because I'm looking at dimension 1. So T is 1. So T is these are all the generators in S, right? And WP is basically this WS. So and edges correspond to so I want a one-dimensional cell for each coset of. I want a one-dimensional cell for each coset of this thing. So a one-dimensional cell, and how do I? This G is representing the coset that I'm looking. Okay, so this is already so far it's already the same as a KV graph. If S was my generating set for my Coxeter group, then this is exactly a KV graph. When do I add two cells? And maybe before we do this, see if I have one more color. In this picture, what are the vertices that I want? The only vertices I'm interested in now are the ones corresponding to the cosets of WP. Those are the only new vertices that I'm interested in. Right? And when do I put and I want an edge. I want an edge between the G was identity, I want an edge between identity and S in some sense. So I have this edge, sorry, this one edge. So these are the only edges I have nothing of the interior. Okay, so I've already gotten rid of the edges which were in the middle. And what are two cells now? Two cells are, I want to define them such that I just throw in one hexagon for this picture. I don't want anything that's in the So what are two cells? Two cells correspond to P having two elements. And WP being this dihedral group, but M has to be less than infinity because I'm looking at spherical ones. I'm looking at the finite ones. And this corresponds to literally the cell I want to put in here now is take all of this and put the cell. That's the cell I want to put in. That's the 2 cell I want to put in. So I've cleaned up my picture. It's literally cleaned it. And then, so what's happening? There are 2 skeletons. The one skeleton was exactly Cayley graph. And the 2 skeleton is exactly what is called a Cayley 2 complex. Cayley 2 complex is literally you take your Cayley graph and then you fill in all the loops and all the relations. And then, okay, let's do one more step. What are 3 cells? For 3 cells, I'm looking at elements like triples, but I want the such that WT is finite. Okay, I want to make sure WT is finite. So then I need to, if I had the list of finite consider groups, I would look into that list and see what are possible things I can have here. But for example, if gamma was gamma t, let's say, if I chose these 3 points, which have no edge between them, in my big subgraph, it's like S, right? There is no edge between them. So remember what it means for there to be no edge. No edge means they commute. So they all commute with each other. So this is a Z mod 2 cross Z mod 2 cross Z mod 2. So this guy in my example is Z mod 2 cube, which is a finite group. And now the question is what 3 cells should I attach corresponding to this? And the 3 cell I want to attach here. It would, so for each pair I would and these things have to be done consistent. I mean, the way I'm defining it, it's all consistent. It will glue nicely to the 1 cells and the 2 cells and so on. So for each pair, I will have so if I have SR, right? If I was just looking at the 2 subset of 2 things, I get this 2 cell. According to if I was just staying here, the 2 cell I would get. So I'm getting a 2 cell for each pair here. I have a 2 cell for each pair, which means I have R S equals to R S P. Okay. Yeah, so I have the RS, I have those 3 faces, sorry.
Okay.
Yeah, but then I want to throw in a 3 cell. I want a 3 cell for every, if P has 3 elements, I want a 3 cell. So I'm going to just complete it into a 3 cell, but let's be careful, let's just write it once. This is R, this is S, this was SR or SP, this is P, so this is R, this is PR, this is PS, and this guy is SRT, but they all commute. So the order doesn't matter. So those are the vertices. And the 3 cell that I'm going to throw in is going to be that cube. I want to throw in that cube there. Okay. Now I want to, okay, so I've told you cells. So far I've told you what cells to look at, but now I have to glue the cells together. Okay, so eventually I want a metric space because eventually I want to prove it's cat 0. So I want to specify a metric on these cells. And once I give you a metric on these cells, then I want to glue them by isometry on the faces. Is what I want. We'll see. Okay, so yeah, since we have 10 minutes, let me tell you how to do the metric. And then when we come back, then we can do examples. Then we can draw some pictures. Um. Okay, so if I have an N cell. Right, what does the N cell correspond to? The N cell corresponds to this Coxeter, the spherical Coxeter group, right? Spherical Coxeter group where the size was N. Um. Okay, more facts which I went through. The finite spherical Coxeter groups are exactly the geometric reflection groups. These are exactly the finite spherical reflection groups. Basically they are acting on SN. Yeah. The examples we were doing earlier. For example, when I have, let's just do. So when I have this dihedral group, this is the picture we were drawing, right? Like I was in S1 and I had this R, and this angle was pi by M. So I want to think about what I want to do is, sorry, I should say code. Give Euclidean metric to each cell. My goal is to give a Euclidean metric because I'm looking to build M0 polyhedral complex. Okay, I want to build this complex by Euclidean pieces, and then eventually I will prove it's Katsian. So how do I? So okay, it's the same example there, right? That hexagon, and I want to come up with a metric for that hexagon. So how am I going to do this? Okay, the spherical polytope was like this thing here, but it's sitting in R2. So what I can do is I can pick a point anywhere in this cone. There is this cone. I can pick a point anywhere. And as soon as I pick this point, let's call it X, I can apply these reflections. Apply these reflections. So this reflection will give me, so this is X, this will be Sx, this will be Dx. And then as I do this again, I will get as I keep doing these reflections, I'll get, so how did I pick this point? Well, I had this distance ds here and dt here. Okay. Like this point X is determined by how far it's from this reflection axis and from this reflection axis. And okay, so what's the total edge length? That's ds plus ds, and this one is 2 dt. That's the metric. That's the metric I want to assign to my like this is my 2 cell, right? And I was trying to decide what metric to give to this 2 cell. And the way I will give a metric to this 2 cell is by this 2 cell. Again, because I'm working with spherical reflection groups now, because of spherical, I can be in some Rn plus 1. And there I have, I was saying I have this cone. I have this cone for S and P. And if I pick any point in here, different points will give me different metrics. But the shape doesn't change. It's still, even if I pick a different point, it will still be a hexagon, but a different metric. So I just want to pick one metric.
How do you ensure that the image SX lie outside the cone?
Because it's a reflection. It's like really in R2, it's a reflection. Yeah.
You are not taking reflection with respect to the line joining original X or?
No. I already have my reflection group. I'm starting with this spherical Coxeter group. The spherical Coxeter group is acting on Sn, but I can pretend Sn is sitting inside Rn plus 1. And so that's the picture I'm doing. So I already have my reflection hyperplanes. And I'm picking a point in that cone which is spanned by those reflection hyperplanes. Yes, to define a metric. And I just choose one. Like I have to pick a metric. Yeah, so what I want to do is, I basically have to specify these numbers, ds and dt. If I specify these numbers, then I've specified metric on with that. Yeah, so fix a vector d in 0 infinity s. Basically, for every element little s, I'm picking a d sub s. And that's going to tell me where this point is in that code. Or basically for every t, every finite and spherical. Yeah, I'm fixing a big vector. I only care about the vector corresponding to t for each spherical t. I get what I call a Coxeter cell. Sigma p dt bar. So basically d bar restricted to t. I'm fixing one vector just so that I can glue things together nicely. That's why I'm fixing one vector. For each wt and now doing these samples along basis. Right, like this wt was st. Maybe I have some other w prime, which is s r with some other n, with some n prime here. So I want, like, there will be an edge connecting, like in my, if I have another, so this was the edge connecting identity to S. And then I have these T's, but I'll have another polygon, which will be, so this was S, T, and this will be R. So I want to make sure that this polygon and this polygon, when I'm supposed to glue them together, they match up. That's why I fix this vector at once. So what exact metric I choose will not really will not affect whether my space will be cat 0 or not. But I still want a metric space eventually. So okay, so last thing. So what did Newsom do? Or no, Davis. I think this is, I'll write Davis and Newsom both. So just summarizing our discussion, for any Coxeter system, WS and a choice of this vector, the Davis complex, this is with sigma WS, admits the structure of a Euclidean polyhedral complex. Such that, so like, what were some nice things? The vertices of sigma were in one-to-one correspondence with the group elements. The one skeleton was in one-to-one correspondence with the Cayley graph. The two skeleton was K2 complex. And then we said something about N cell. We knew exactly where N cell comes from. Each N cell. Sorry, I'm not writing it. Each N cell came from a spherical. Each N cell came from WP spherical. And this is one of the most important bullet points, which I will not going to prove, that the link of every vertex. Link of every vertex is this L. This L subcomplex which we defined in the beginning. So you know what the link of every vertex looks like. And the coset of cells is, yeah, originally we defined this thing, right? We defined these partially ordered sets, and then we had K, L, and this W, S. So what, and then I did this new definition. What's the relationship between this new definition and the old definition? If I look at the partially ordered set of cells of this new guy, that's exactly the old guy. Okay, in the hexagon, if this is my hexagon, if you want to do the partially ordered set of its cells, so well, for each vertex, I give myself a cell, but then for each edge, I have to give myself a vertex also. For each edge, I give myself a vertex, and for each two cell, I give myself a vertex. And then I have to join them because there is containment. So that's the relationship between these two. And this link condition is very important because maybe like in the next hour, I can tell you, this gives you a lot of freedom. So the link can be basically any flat complex. The link can be any flat complex, and then using that, Davis proved a bunch of things in geometry and topology. So maybe I'll tell you what he did with this. He did some really amazing theorems. I'll tell you that in the plan for the next hour, because we have 1 hour after the tea break. So first there are some exercises on Davis form. So it would be nice if you can like try to draw some Davis complex and prove another important thing. The oxidar group is acting properly discontinuously compactly on the space. So proving that that's true, that's also an exercise. Yeah, so we'll come back, mostly spend time doing those, and then maybe in the last 15-20 minutes, I'll say something more about it. I'll just wrap up. Yeah, so in the last 20 minutes, I'll try to wrap up what we've been doing. Okay. Spherical means that it's finite. The subgroup is a finite.
Yeah.
Yeah, sorry, I defined it earlier. I should have defined it. Yeah.
In fact, so basically,
That's supposed to be the finite. Yeah. Meanings here also. Like of this one. This.
रेसिच्या पेपर मध्ये मी तुला विचारलं मला इथं सगळे रिझल्ट्स हवे एक्स्ट्रीम
Yeah, yeah. I have to do it for everything.
नाही तो तर माझ्याकडे कॅरेक्टर रिलेशन व्हॉट्सअप माझ्या रिझल्ट नाही भेटले मला ऍक्च्युली तो नॅचरल वाटतो कारण की तो पीडी फंक्शन्स मध्ये तोच वापरतो सारखा उल्शास की तेच लोक First one. 89 and I'm choosing to create video proof for पेपर में पब्लिशर्स लिखना होता है करंट में खूप कॉम्प्लिकेटेड कुठे झाला एक तासाचं डिस्कशन म्हणजे
Can we really provide that from the cases? No, I don't know. If I look at this thing, if I look at this building, there's another, we might access. A building is defined as a. Occidental growth valued matrix space, whatever it is. We are mapping from X cross X to. So how to bound that, that's a big thing. Yeah, I think it's much more geometry, much more topology. That will probably.
Right.
I think.
Yeah. I'll get my phone.